Okay, good afternoon. Let's look at example of Thevenin, and then we'll look at the last strategy number 3 on trying to find Thevenin and Norton equivalent circuits. And then we'll go into superposition. All right, so we had stopped here. The discussion was about Thevenin and Norton equivalent circuits. And this technique can be applied to any linear circuit. Linear circuit means comprised of linear sources and linear components. Typically, there would be current sources, voltage sources, and resistors. So if you have a circuit inside, let's say, a sealed box, we can represent the entire network as a single voltage source or as a single current source. If you wish to find the voltage, all you are doing is we are taking the measurement terminals and measuring the open voltage or the open circuit voltage between those terminals. That's our Thevenin voltage. If you want to find Norton current between those same terminals, we place a short circuit wire, and then we calculate or analyze the circuit to determine the current flowing in that wire. And that would be our Norton current, IN. And then if we wish to find Req, or sorry, Thevenin resistance, then we simply find Req for that network. Okay, so just a second. Examples not given here. Okay, so here is the shortcut method of finding RTH, because the relationship between the three quantities is given by Ohm's law. VTH is equal to IN times RTH. So if you have any two of the three quantities, you can calculate the third. But again, this is not a technique that I prefer or advise for the students. It's because if one of your two quantities is incorrect, then your third one is also incorrect. Okay. So in a quiz or in an exam, I would never ask you to use the shortcut method. Okay. You always find each one of these quantities independently. And the way we find RTH is by calculating REQ. Calculating REQ between those same two terminals. Okay. But in order to do that, we cannot have any sources left in the circuit. Okay. We have to deactivate and remove those sources from the circuit before we can measure or calculate REQ. Make sure I'm on the right one. Yep. Yeah. Which one? No, that's a standard procedure. That's one of the standard procedures. It's called deactivate the sources. Deactivate could also mean reduce the sources to 0. Deactivating the sources means reducing the source to 0. In this instance, deactivating does not mean just turning it off. Okay. Deactivating or reducing a source to 0 means something else. What we are doing is we are removing the sources from the circuit. Every place where you have a current source, let me write it. Replace voltage source with a short circuit wire. And replace current source or current sources with an open circuit. Okay. Replace voltage sources with a short circuit wire and replace current sources with open circuit. And then we can calculate Req, because then all we have left in the circuit are a bunch of resistors. Then we find Req. So replacing voltage source with a short circuit wire would look something like this. You remove the voltage source in the circuit, and in its place, you connect a wire. That's all. Essentially, just looks like both those nodes are now connected to each other. What if it is a current source? What do you do? Exactly. You remove it and you replace with an open circuit, meaning there's nothing, you simply remove it. That's all it means. So the circuit could just be left like this. All right, any questions? Pause, think over it. Let me know if you have any questions. These are important concepts, okay, in electrical engineering, in physics, in circuit analysis. Reducing or deactivating a source is an important concept. So anytime you hear or read the words deactivate, reduce, or reduce to zero, that's what it means. And now when you do that, circuit connections in a circuit will change. Previously, if you had two resistors connected at either end of the voltage source, they are now connected together because the voltage source is gone and there's a wire in its place. So now those resistors would be in series. Same thing with the current source. If there was a current source in place as in a pathway in a circuit, if you remove it, it could change the circuit. Resistors could become connected or disconnected from the rest of the circuit. So circuit changes, and then we find Req. Okay, and that Req is your Thevenin resistance or Norton resistance. Okay, RTH or RN. And once you have that, then you can use Ohm's law to verify. Because you have independently calculated all three quantities. If one of them doesn't match, then you know which one is the problem. Okay. All right, let me know if you have any questions. Yes. Good question. Why do we replace current sources with an open, and why do we replace voltage sources with a short? The key word here is reduce the source to zero. Reducing a source to zero means if it's a voltage source Vs with a value of, let's say, 10 volts. Okay. The only way the voltage between those 2 points would be zero is if they are both at the exact same potential. And in order to do that, we can short those 2 points together. Hence, we short it. So if you short it, then the voltage between those 2 points is now equal to zero. So you say we have reduced the voltage sources to zero. Current source is the same thing. The only way to ensure that 0 amps of current is flowing through is to take away the pathway. So if you remove the pathway for the current to flow through, no matter what value it had previously, 1 amp or 100 amps, now it's 0 because there is no pathway for it to flow. And so that's why we replace it with an open and a short. Again, important concepts. Okay, then let's look at how we can calculate the open circuit voltage for this example. So we have 5.1K and 3.3K, and we are trying to find the open circuit voltage. That open circuit voltage has 2 wires coming out, okay? But those are just wires. There is no component connected to it. A wire is simply an extension cord. It doesn't mean anything. It has 0 ohm resistance, and it's not connected to anything, so there's no pathway for current to flow through. So if you're measuring VOC between those terminals, effectively, we are measuring the voltage across that resistor, across the 3.3 kilo ohm resistor. Does everybody see that? Right? Because those 2 points are in parallel. So if you're trying to measure the open circuit voltage at the output terminals, effectively what we're doing is you're trying to measure the voltage across that 3.3 kilo ohm resistor. And we can find that value by applying Ohm's law. It's a series circuit. Current flows in this direction. Total resistance in the pathway is 8.4. We calculate the current I. I is 10 divided by 8.4 kilo ohms. Once we find the I, we multiply it with the 3.3. So we applied Ohm's law first to find the current I, and then we applied a second time to find the voltage. And that voltage is our Thevenin voltage. Yeah, let's take a pause. Let me know if you have any questions. Okay. It's just repeated applications of Ohm's law, KVL, KCL. Those are the only 3 analysis techniques we need. Okay. And we can derive the rest from these 3. Make sense? Okay. ISC. For ISC, we take the same 2 pairs of terminals and we place a short circuit wire between them in order for the current to pass through. Okay. And the current that's passing through that wire is our short circuit current. So take about 10 to 15 seconds, look at the circuit diagram and tell me how has it changed. We placed a short circuit in there. How has it changed? Or what has changed because of that short circuit? So yes, absolutely. The concept here is, what is the, well, let's back up a bit. What is the resistance of a short circuit wire? 0. It's 0 ohms. And where is it connected? It's connected directly across the 3.3 kilo ohm resistor. So they are effectively in parallel. Now, let's say you're driving down a street. You want to cross over to the other street. So that's running in parallel to yours, and you have two alleyways to go through. If one of them's clogged, or if there's even a little bit of traffic, and the other one has no traffic, completely wide open, which path do you take? The one that's wide open, right? So a short circuit is effectively wide open. Theoretical analysis, it means it has 0 ohm resistance. If it is 0 ohm resistance, it doesn't matter what is connected in parallel. Nothing will go down the other pathways. Everything is going to flow through that 0 ohm pathway. So if there's current coming from our source, comes down here, comes through here, well, it should go through here and here, but because the resistance is 0 on the right, everything is going down here. Nothing will go here. So effectively, anything that is in parallel with a short circuit wire is redundant. It may as well not be part of the circuit at all. It is effectively removed from the circuit. Again, this is an important concept that you need to use in circuit analysis. You'll encounter these often. So if you have a short circuit anywhere in your circuit, anything that is in between those two nodes is effectively removed from the circuit. Okay, so that's an important concept. All right, let me know if anyone has any questions. Does that make sense to everyone? Yes. Question being asked is, can we see an example with a current source? Yeah, we can. If I change this to a current, then make it even easier, just because I just apply Ohm's law once and find the answer that way. I can find, let's see, this example. It's not on this one. But I can find one easily. It's not, those are not uncommon. Okay, so we apply Ohm's law. The only resistor in the pathway is 5.1, and all of that current is going to go through that short circuit wire. That means our ISC can be obtained by direct application of Ohm's law. So 1.96 milliamps. And that means our Norton current is 1.96. Okay, it's 1.96. Does that make sense? Okay. And then in the slide, we have an application of Ohm's law again. So to find the RTH and RN, which is 2 kilo ohms. But instead of doing that, let me solve it using the technique we just outlined by finding REQ. So my original circuit is this. I have a 10-volt source, 2 resistors, and I want to find RTH between these terminals. Well, in order to find RTH, what do? We find REQ. In order to find REQ, there must not be any sources present in the circuit. So we reduce them to 0. In this case, voltage source, we short it out. And now, take out your calculators and tell me what is the REQ between these 3 points, or between these 2 points. First, take 10-15 seconds to see how the circuit has changed and how we can find REQ. Are they in series? Are they in parallel? Anyone? Are they neither in series nor in parallel? Sorry, someone was. They seem to be in series. It's a unique circuit when you have two components. They are in series as well as they are in parallel, as with regards to voltage and current. However, if we are trying to find Req is measured between 2 points. And between those 2 points, we have 5.1 connected at this point, right here at the top. And 3.3K is also connected at the other end. And so they are effectively in parallel because both their nodes are connected to the respective measurement terminals. And so I can redraw this circuit like this. So yeah, the connection is in series because they're only connected at one terminal on both ends. But in order for it to actually be in series, we'd have to remove one of those connections and then measure between those two open connections. But that's not what we have here. We have an Req measured in there. And so our short somewhere there. So what is the answer for 5.1K and 3.3K in parallel? Which we can now verify. Did you really calculate or you just say it because it's okay, great. It's 1.9 or how much? My eyes are not that good. I can't. 2.0035. So yeah, that's 2 kilo ohms. But while we're on that subject, 2.0035, right? So 2 zeros. So it's actually 2003.5 ohms. So just as on a tangent, on a little bit of a side note, this is why decimal places matter. If you have a unit prefix that is 10 raised to 3, that is 10 raised to 6, right? And we just say, okay, 2.003. Well, 2.003K is 2003 point something. And so sometimes in calculations, it makes a big difference. So I usually take decimal places depending on the unit prefix. If it's like 10 raised to 6 or 10 raised to 9 or something, then I go as far out with my decimal places as many as possible. Okay. Otherwise, it sometimes causes issues. But anyway, so you obtained, let's 2.0035 ohms, which is what we had directly. So now if we have VSC, VTH, RTH, and IN all calculated separately, we can verify our answer by using Ohm's law. And then we can know for sure, for certain, that our analysis is correct. Okay. All right, any questions? All good? Okay. All right. Thevenin of a voltage divider. This is something that we will encounter often in circuits. So it doesn't matter what kind of circuit it is. Sometimes we have a voltage source, we have multiple resistors in there, and we need to find the Thevenin equivalent circuit. Well, the easiest way to do that is by applying these equations. The equations come about, we already saw this, right? RTH is R1 parallel R2. We just saw it on the previous slide, right? Right here. Right? Req, RTH is those two resistors in parallel. So RTH is R1 parallel R2. In VTH, we can apply a technique known as voltage division. Voltage division is derived from Ohm's law. We know that the current flowing through this circuit would be I. I is V over R1 plus R2. And then we apply voltage or Ohm's law again. VR1 is I times R1. So it's V over R1 plus R2 times R1. We rearrange the terms, and what do we get? VR1 is equal to times your source voltage V. Let's take a pause while you go through that. Let me know if you have any questions. It's a repeated applications of Ohm's law, right? You apply Ohm's law here. Yes. That makes sense. This technique is known as voltage division. You can apply this technique to any series connected resistive network. Okay. If you have a series connection of resistors, you can apply voltage division, because what is R1 plus R2? Between these 2 points, as seen by the voltage source, R1 plus R2 is the REQ of that series connection. This REQ is different, okay? We are not measuring from the output terminals. We are measuring from the voltage source. So if you remove the voltage source and you measure REQ, you have your 2 resistors in series. That is your REQ. So voltage division states that you can find the voltage across any resistor in a series network of resistors by taking the ratio of the resistor to REQ. Okay, so it's R1 over REQ into V, the source voltage. Similarly, VR2 would be R2 or REQ into V. This REQ So this is not the same REQ because the measurement terminals are different. Okay, the measurement terminals are different. That's why it's not the same REQ. Okay, anyway, so this is something that you'd have to commit to memory and keep it in mind. If you have 2 or 3 resistors connected in series to a voltage source, then you can use these equations to quickly determine the Thevenin equivalent that is being applied to the circuit. Okay. So in the 3 methods to find, we actually did the 3rd method. The voltage source with 0 value is replaced with a short circuit. Current source with 0 value is replaced with an open circuit, and you find Req by deactivating the source. Okay. All right. You can look at these two slides and review them and see how much you know so far. Let's see. This is for student reading, so. And there's a student exercise home. It's not a homework that you need to submit, but it's a home exercise at the end. All right, principle of superposition. How many of you have heard of superposition before in physics? Yeah. So superposition applies to linear circuits. What it states is, if you have a circuit comprising of multiple sources, including voltage and current sources, all of them together, you can analyze the circuit piece by piece. You can break it up into multiple parts, analyze the circuit for each individual part, and then calculate the voltages and currents that appear in the circuit due to only one source active at a time. Then if you sum them all up, that would give you the actual voltage and current. Okay. The superposition states the voltage or current appearing, the voltage and currents appearing at any point in a circuit, they are the result of all of the sources acting at the same time or working at the same time. So if you have like 2 or 3 voltage sources and 5 or 6 current sources, all of them together in one circuit, if you try to find the voltage at any single point in a circuit, the voltage at that point is a result of all of those all of those sources working together. Okay, that's what the principle is. So if you wish to analyze it, we can do a little bit of reverse engineering. If they're all working together and it results in a voltage of 5.6 volts, it stands to reason that if I analyze them with only one working at a time, I would get voltage for each source. And then if I sum up those voltages values, it should result in 5.6 volts. So superposition applies to linear circuits with linear components. And break it up into multiple parts. Now, when I say breaking it up, does not mean that you're just separating out the components. That's not what we are doing. What we do in superposition is we keep the circuit components as they are, but we deactivated all the sources. So breaking up the circuit means analyze the circuit, the exact same circuit, with only one source active at a time. Okay, only one source active at a time. If you have 4 sources in the circuit and you wish to find voltage at one single point, you have to analyze and find 4 values for that voltage for one of those sources at a single time. This results in simplification of the network analysis, right? You can simplify your analysis However, the more number of sources you have, the more analyses you have to perform. And so the downside to this is if you have multiple sources in a circuit, it is simpler and easier to analyze with superposition. However, it is far longer than any other method. Right? For every quantity, you have to perform multiple analyses. Does that make sense to everyone? So in this example, we have two voltage sources, two resistors in series, and one 30 kilo ohm resistor in parallel. If you want to find the Thevenin equivalent circuit for this one, for this circuit diagram, we have our output terminals right here. Let's call them A and B. This A and B, what do we see between A and B? I'm going to redraw this in a way that'll make it a little bit easier. This is A and this is B. Would you agree? Right? This is 2 volts. This is 10 kilo ohms. Then we have 30 kilo ohms on the far right somewhere. So how about the other source? What do we see? We see that the negative end of the source is connected to B, right? It's connected to B. And then the other end is connected to the resistor, and the resistor is connected all the way to A. That's what the circuit actually looks like. Just a matter of drawing it differently. So always keep redrawing the circuit until it starts making sense to you. Okay. So if I wish to find RTH between A and B, what do? We short out the voltage sources. So we short it out. What do we have? 3 resistors in parallel. Answer is right there. You can solve that later on. Right? Deactivated all the sources, placed a short circuit for the voltage source. Everything is in parallel. So my RTH is 10, 20, and 30 kilo ohm resistors in parallel. But what if I now want to find voltage? What do? Well, if I wish to solve it using superposition, I have to analyze it with only one source active at a time. So this is what I'm going to do. This is the 2-volt source, and I'm going to reduce the 3-volt source to 0. So replace it with a short circuit. The 3-volt source, it was here. Now it's replaced. So A and B. Analyze for the open circuit voltage between A and B. And what do we have? We can apply voltage division because this circuit can be reduced. 1 resistor, 2 resistor, and A and B. This is 20K, 30K. This is 10K. So this is 20K in parallel with the 30K. And now I can apply voltage division to this. So voltage division would give me, better find the voltage across the 20 and 30 in parallel combination. So V1 is that resistor divided by the Req. In this case, it's still the same circuit that we saw previously. Two resistors in series. We're trying to find the voltage across A and B, which is the the resistance. The Req would be 10K plus the parallel combination of 20 and 30. Because they are in series, we're trying to find the voltage across that bottom resistor. And hence, we can apply this equation. So Req in this case, simply 10K plus 30K in parallel. We calculate that, we come out to 1.09 volts. Now, the other source also is a voltage source connected similarly in parallel. So if I wish to find the voltage using that source, it still be the same thing, except now the 2-volt source is reduced to 0. The 3-volt source is active. But the circuit has not changed because as far as the circuit is concerned, you still have 10K, you have two resistors in parallel, and it reduces down to exact same as the one above. And if that's the case, then you can apply the same technique, find voltage division, or apply voltage division, find the voltage. And then you have two different voltages for V1. Sorry, not V1. There are two different voltages at the output terminal. So VAB has two values. Let's take a pause while you write that down. Let me know if you have any questions. Yes. Yep. Everything is different. There is no fixed answer. It's like we look at the circuit, and then circuit has changed in several ways. So there's no fixed approach. Okay. So the important point here is not how we solve it after. The important point is how we apply superposition before we even begin solving it. To set up the solution correctly, we have to apply superposition correctly. If the superposition is not applied correctly, then the rest of it does not matter. Okay. So we have two voltages, 1.09 and 0.82. They're both have the polarity in the same direction. So in order to find the actual Thevenin voltage, we need to sum up both those voltages. So 1.09 plus 0.82. So our actual Thevenin voltage is 1.91 volts. In order to find just one quantity, just one voltage, we had to set up the circuit and analyze it 2 different times, or analyze it separately. Okay, and that's the downside of applying superposition. If you have two sources, you need to calculate every quantity twice. If you have 3, you have to calculate every quantity 3 times. If it's 4, then 4 times, and so on and so forth. So every additional source will require an additional analysis. So it makes it simpler, but it's time consuming. Or it can be time consuming depending on how big the circuit is. All right, any questions? Okay. Take some time to review the lecture video and the slides right after class if you have time. If not right after class, then at least later today if you can, because these are all important concepts and you've gone over quite a few things. Okay. As practice, yes. Practice problems. Okay. So I will post the homework problems later tonight for homework 2. That will not be due until like next Sunday. So you have 8 days, 8, 9, yeah, more than a week to get it done. Okay. And then LT Spice, I'm assuming everybody has LT Spice on their personal devices by now. And then the next 2 slides are of simulating the same circuit with LT Spice. Okay. Everybody's familiar with the .op command by now, .op.dc, right? Okay. So you can apply that. And then here, it's not class activity. It's home activity. You can work with other people. You can work by yourself. You can work in a group. That is fine. Anything goes for this. But just find the current I using superposition. And it's 3 resistors, 2 sources. Okay, so it's not too complicated. And then once you're done, you can also verify your answer with circuit analysis tools. Okay, do not simply use LT Spice to find the answers first. That would kind of defeat the purpose of you learning. That would defeat your own learning. So don't simulate it first, right? Manually. If you get stuck, you let me know. I'll be available I have a few things going on over the weekend, but I should still be able to respond via email. So if anything happens, you send me a screenshot image of your work and I can troubleshoot and respond via email. Okay. So again, first, prime manual solution, then software. Okay. All right. Any questions? All right. If there are no questions, we'll end class here today. I will see you all on Monday. And I will post homework 2 later tonight in a few hours. And then quiz on Monday based on the work that we have done this week. So mostly it'll be about concept of Thevenin and Norton, and then perhaps a small problem or 2. Okay. Problems will be somewhat similar to what we have just seen in class. No different.